Okie doke. Let's see. Okay, I wanted to read the prenatal development paper, but I have not finished that article yet, so I want to hold off on that. Let's find another article to read. So we did information bottleneck, did visualizing loss landscape. Ooh, I have not read Atom, and that is an optimization method used everywhere, so that'd be good. Let's see. I only did the first page. Okay, this is okay, just 9 pages, not bad. Okay. See, Atom, a method for stochastic optimization. Let's see, already read all this. Okay, just to lead off. Yeah, some of Atom's advantages are that the magnitude of parameter updates are invariant to rescaling of the gradient. Step sizes are approximately bounded by the step size hyperparameter. It does not require a stationary objective. It works with sparse gradients, and it naturally performs a form of step size annealing. Let's see. In section 2, we describe the algorithm and the properties of its update rules. Section 3 explains our initialization bias correction technique, and section 4 provides a theoretical analysis of Atom's convergence in online convex programming. Empirically, our method consistently outperforms other methods for a variety of models and datasets, as shown in section 6. Overall, we show that Atom is a versatile algorithm that scales to large-scale, high-dimensional machine learning problems, which is why it's used everywhere. Let's see. Although I seem to remember seeing mention that using batch norm layers reduces the benefit of Atom compared with other methods, but I might be getting that confused with another optimization technique. Okay, algorithm. The algorithm 1 for pseudocode for our proposed algorithm. Atom. Okay, let f of theta be a noisy objective function, stochastic scalar function that is differentiable with respect to parameters theta. We are interested in minimizing the expected value of this function. Oh god, I misprinted all this bullshit. I gotta pull up the digital version. Yeah, let's see which one. What? Did I not put it in my folder? Oh, that may have been one of the ones we need to continue. Oh, okay, freaking open. Okay, downloads, to print, no, to print to continue. No, huh. Oh wait, didn't we finish printing information bottleneck? Let's see, all the way up to page. Yeah, it's got the whole index. So, yeah. We'll move that to the AI folder. Let's see, yeah, formal algorithms for transformers. Not put Atom in here? Training. Nope. Did I really delete the Atom paper? guess I'll have to re-download it. Oops. Let's see, what was the arxiv? Yeah, there we go. Method. Oh, no, come back. Okay. So version. Oh, wait a second. This is version 2 and this is version 9. Hmm. Hmm. Good, we do have version 9. Move that to AI. Okay. See, page 2. Okay, yeah, expectation value of x. Okay. That's expectation value. Good, gets that. Function of theta with respect to its parameters theta with f sub 1 of theta all the way to f sub t of theta. We denote the realizations of the stochastic function at subsequent time steps 1 through t. Stochasticity might come from the evaluation of random subsamples, many batches of data points, or arise from inherent function noise with g sub t equal to the gradient with respect to the theta of the function. We denote the gradient, i.e. the vector partial derivatives of f sub t with respect to theta evaluated at time sub t. Right, that's all normal so far. Expectation value. The algorithm updates exponential moving averages of the gradient m sub t and the squared gradient v sub t, where the hyperparameters beta 1, beta 2 are members of the set from 0 inclusive to 1 exclusive. Okay. Control the exponential decay rates. Okay, yeah. Exponential decay rates of those moving averages. The moving averages themselves are estimates of the first moment, the mean, and the second raw moment, the uncentered variance of the gradient. However, these moving averages are initialized as vectors of zeros, leading to moment estimates that are biased towards 0, especially during the initial time steps, and especially when the decay rates are small, i.e. betas are close to 1. The good news is that this initialization bias can be easily counteracted, resulting in bias-corrected estimates n sub t and v sub t hat. See section 3 for details. Okay, square gradient m sub t, square gradient v sub t, hyperparameters, beta 1, beta 2. Okay, these moving averages are estimates of first moment, the mean, the second raw moment, uncentered variance. Note that the efficiency of the algorithm 1 can, at the expense of clarity, be improved upon by changing the order of computation, e.g., by replacing the last 3 lines in the loop with the following lines. Okay. Yeah, it's alpha t equals alpha dot square root of 1 minus beta 2 all over 1 minus beta 1. And then theta t is that the parameters at time step t are modified by the previous parameters minus alpha times the moment, the mean, all over the square root of vt plus epsilon hat. Where does epsilon hat come from? Oh, okay, it's control. Epsilon, wait, epsilon, is that the same epsilon hat? Is that? No, okay, that's just epsilon. Where does the hat come from? Where are we getting the estimate? Oh. Okay, let's see. Adams. What does that actually say? Adams update rule. Adams update rule. Okay. Important property. Oh my goodness, these freaking A's. An important property of Adams update rule is its careful choice of step sizes, assuming epsilon equals 0. The effective step taken in parameter space at time step t is, oh my god, delta t. The alpha, yeah, alpha times delta t. So taking parameter space at time step t is delta t equals alpha times the mean of t hat, so the estimate of all over square root the variance or the velocity estimate at time t. The effective step size has two upper bounds. The magnitude of delta t must be less than or equal to alpha times 1 minus beta 1 all over square root of 1 minus beta 2. In the case 1 minus beta 1 is greater than square root of 1 minus beta 2, delta t is less than or equal to a. Otherwise, oh, gotcha. Okay. So we could rewrite this as upper bound delta t is less than or equal to c alpha dot 1 minus beta 1 all over square root of 1 minus beta 2 in the case given that 1 minus beta 1 greater than square root of 1 minus beta 2. And then same thing, delta t is equal to alpha times all other cases. It's just a fixed ratio. If the numerator is greater, then we multiply. If the denominator is greater, then we just drop it, the term. And delta t is always, so delta t is always less than or equal to a in the other case. The terms just disappear, huh? First case only happens in the most severe case of sparsity. The gradient has been 0 at all time steps except the gradient has been 0 at all time steps except at the current time step. For less sparse cases, the effective step size will be smaller. When 1 minus beta 1 equals the square root of 1 minus beta 2, we have that the momentum over the velocity or the variance is less than 1, therefore delta t is less than alpha, right? In more common scenarios, we'll have that momentum t over variance is approximate to plus or minus 1, since the expectation value of g all over the square root of the expectation value of g squared is less than 1. What? see, where is epsilon hat? Okay, so there's GT, right? Get gradients. MT update bias first moment. B of T update bias second row moment. Compute bias corrected first moment estimate. Compute bias corrected second row moment estimate. And then we update the parameters. We're doing multiple iterations per epoch until it converges. So we're actually updating the parameters multiple times. So it's actually a very expensive algorithm, but still converges more quickly. Just how good the momentum analogy is, I guess. See, the effective magnitude of the steps taken in parameter space at each time step are approximately bounded by the step size setting alpha, i.e. magnitude of delta t is less than or equal to or approximately alpha. This can be understood as establishing a trust region around the current parameter value, beyond which the current gradient estimate does not provide sufficient information. Yeah. Okay. I like that. This typically makes it relatively easy to know the right scale of, what is that character? It's missing. Ugh. It's easy. All right, it's got alpha in advance. For many machine learning models, for instance, we often know in advance that good optima are with high probability within some set region in parameter space. It is not uncommon, for example, to have a prior distribution over the parameters. Since alpha sets an upper bound of the magnitude of steps in parameter space, we can often deduce the right order of magnitude of alpha such that optima can be reached from theta 0 within some number of iterations. With a slight abuse of terminology, we will call the ratio m sub t hat over square root of e sub t hat, the signal to noise ratio. With a smaller signal to noise ratio, the effective step size delta t will be closer to 0. This is a desirable property since a smaller signal to noise ratio means that there is a greater uncertainty about whether the direction m sub t hat corresponds to the direction of the true gradient. For example, the signal to noise ratio value typically becomes closer to 0 towards an optimum, leading to smaller effective steps in parameter space, a form of automatic annealing. The effective step size, delta t, is also invariant to the scale of the gradient. So rescaling the gradients g with factor c will scale m sub t hat with a factor c and v sub t hat with a factor c squared, which cancel out. Yeah. Very cool. Okay, now, for example, the signal to noise ratio value typically becomes closer to 0 towards an optimum. Signal to noise, not noise to noise. Wait. Signal to noise becomes closer to 0? So the noise increases and the signal decreases as we get closer to an optimum. That seems the opposite. With a slight abuse of terminology, we will call the ratio the signal to noise ratio. Okay, so they're acknowledging it's a little bit misleading. So with MT, Gee. Oh man. We have to get the stats for every iteration. It's an insane amount of computation. Okay. Sorry, getting distracted. As explained in section 2, Adam utilizes, I've got to correct these typos. Adam utilizes initialization bias correction terms. We'll here derive the term for the second moment estimate. The derivation for the first moment estimate is completely analogous. Let G be the gradient of the stochastic objective f, and we wish to estimate its second raw moment uncentered variance using exponential moving average of the squared gradient with decay rate beta 2. Let G sub 1 all the way to G sub t be the gradients at subsequent time steps, each a draw from an underlying gradient distribution. Is that the correct symbol? Is that another typo? Yeah, okay, or misprint. Okay, so G sub t is proportional to probability of G of t? Is that what that is? Is that what the p function? I don't remember the p function being mentioned previously. Are they just relying on us to assume that's probability? Yeah, I don't see it mentioned anywhere. G. Okay, let G be the gradient of the stochastic objective function f, and we wish to estimate second raw moment. Each draw from an underlying gradient distribution. U of t proportional to probability G of t. Okay, it must be probability. Let us initialize the exponential moving average as v sub 0, or v naught equals 0, a vector of zeros. First note that the update at time step t of the exponential moving average v sub t equals beta 2 times v sub t minus 1 plus 1 minus beta 2 all times g sub t squared, where g sub t squared indicates the element-wise pairs, element-wise square gt. Oh, so the Hadamard product? Yeah. Hadamard. Hadamard or Hadam? What is it? Hadamard. Yeah, Hadamard product. Okay. We written as a function of the gradients at all previous time steps. V sub t equals 1 minus v2, sum of t1 over the all times. Beta 2. Oh, at time step t. Minus I. Yeah. So starting out 1. Let me look at the algorithm again. We've got our step size. We've got our hyperparameters of step size, beta 1, beta 2. We've got our function, our input function, our initial parameters. Then we're going to initialize the moment, the raw moment 1 and raw moment 2. And then time step 0. And then yeah, so it starts at time step 1. Calculate the gradient of the parameters. Yeah, the entire gradient. So, okay, that's the gradient with respect to the parameters. So that's the entire, it's the entire gradient across the whole model, which we assign to gt, and which we scale by 1 minus beta 1 and 1 minus beta 2, and sum with each of the moment vectors that we're accumulating, and then compute the bias corrected moment and second moment scaled by 1 minus beta t Yeah, 1 minus beta 1 and 1 minus beta 2. And once we have those estimates, then we adjust with epsilon to prevent division by 0. Hmm. Hmm. Square root VT. So yeah, these are all going element-wise. Okay. Let's see. We wish to know how. Where'd the paper go? Oh, yeah, expectation. We wish to know how expectation value of VT, the expected value of moving average times of t, relates to the true second moment. Which is the expectation value of g of t squared. So we can correct for the discrepancy between the two. Taking expectations to the left hand and right hand sides of equation 1. Because it becomes the expectation value. T is equal to, should be equal to the expectation value of, all that. Simplifies. Where if the true second moment epsilon g sub I squared is stationary, otherwise can be kept small since the exponential decay rate beta 1 can and should be chosen such that the exponential moving average assigns small weights to gradients too far in the past. What is left in the term 1 minus beta 2, which is caused by initializing the running average of zeros in algorithm 1, we therefore divide by this term to correct the initialization bias. In case of sparse gradients, for a reliable estimate of the second moment, one needs to average over many gradients by choosing a small value beta 2. However, it is exactly this case of small beta 2 where a lack of initialization bias correction would lead to initial subs that are much larger. Okay, convergence now. So, okay, I was wondering about the convergence. We analyze the convergence of atom using the online learning framework proposed in Sinkovich 2003. Given an arbitrary unknown sequence of convex cost functions, f1 of theta through to ft of theta, at each time t, our goal is to predict the parameter theta t and evaluate it on a previously unknown cost function f sub t. Since the nature of the sequence is unknown in advance, we evaluate our algorithm using the regret that is the sum of all previous differences between the online prediction f sub t of theta and the best fixed point parameter from a feasible set x for all previous steps. Concretely, the regret is defined as yeah. I mean, best fixed point parameter. The best fixed point parameter is the lowest that's been found so far. Got the online prediction. Best fixed point parameter. Feasible set x for all previous steps. See where theta star is equal to argmin theta member of x, which is the summing. See, from time step 1 to time step t, it evaluates the online function arcmin theta member x. Where, oh, is that, is it a misprint? Where is that? Show that atom has big O square root t regret bound, and a proof is given in the appendix. Our result is comparable to the best known bound for this general convex online learning problem. We also use some definitions to simplify our notation where g sub t is equivalent to gradient with respect to the function t, and g sub ti as the ith element. We define g sub 1 2t of I member of the reals as a vector that contains the ith dimension of the gradients over all iterations till t. G sub 1 to t I equals so we define, what symbol is that? Greek alphabet. Oh, gamma. Is that gamma? Wait. This is a little curlier, but I guess it is gamma. Yeah, gamma proportional to second beta 2. Oh, yeah, that's another misprint. Yeah, beta 1 squared over square root of beta 2. Our following theorem holds when learning rate alpha t is decaying at a rate of t to the negative half in first moment running. So the inverse of the square. It could just, well, whatever. In first moment running average coefficient beta 1 t decay exponentially with lambda that is typically close to 1, e.g. 1 minus 10 to the negative 8. Oh my goodness. Yeah, I want to assume it's that function. Oh, I'll eat later. Theorem 4.1. Assume that the function f of t has bounding gradients, magnitude, gradient f of t theta less than or equal to g, magnitude f of t theta less than or equal to g infinity for all theta members are dimension of the reals in dimension d, and distance between any theta t generated by atom is bounded. My goodness. D theta m minus theta n for any m members of 1 to t, and beta 1, beta 2 members of, satisfy. A over square root of t and beta 1 t equals beta 1 gamma to the power t minus 1, where gamma is member of 0 to 1 on the open set. The atom achieves the following guarantee for all t greater than 1. Our theorem 4.1 implies when the data features are sparse and bounded gradients, the summation term can be much smaller than its upper bound. In particular, if the class of function and data features are in the form of section 1.2, their results for the expected value also apply to atom. In particular, the adaptive methods such as atom and AdaGrad can achieve big O log of d times the square root of t. an improvement over big square root of dt for the non-adaptive method. The log is better than the square root. Decaying beta 1 t towards 0 is important in our theoretical analysis and also matches previous empirical findings. E.g., says Cover et al. 2013 suggests reducing the momentum coefficient in the end of training can improve convergence. Finally, we can show the average grade of atom converges. More typos or misprints. Assume. Let me scroll down. Assume. Where is it? Page 4. Yeah. Corollary. Okay. Assume that the function f of t has bounding gradients. All parameters. All parameters, remember the reals of dimension d and distance between all t greater than or equal to 1. The regret of t over t equals big O 1 over square root of t. This result can be obtained by using theorem 4.1. Thus, the limit of t as it approaches infinity equals 0. I'm not missing any symbols, no misprints. Some weird gaps there, but okay. Let's see. Related work. Optimization methods bearing a direct relation to atom are RMS prop and AdaGrad. These relationships are discussed below. Other stochastic optimization methods include VSGD, some kind of maybe varying stochastic gradient descent, AdaDelta, and the natural Newton method from Roux and Fitzgibbon 2010, all setting step sizes by estimating curvature from first order information. The sum of functions optimizer, Sol Dickinson et al. 2014, is a quasi-Newton method based on mini batches, but unlike Atom, has memory requirements linear in the number of mini batch partitions of a dataset, which is often infeasible on memory constrained systems such as the GPU. Like natural gradient descent, Atom employs a preconditioner that adapts to the geometry of the data. Since V sub t hat is an approximation to the diagonal of the Fisher information matrix. However, Atom's preconditioner, like AdaGrad's, is more conservative in its addition than vanilla natural gradient descent by preconditioning with the square root of the inverse of the diagonal Fisher information matrix approximation. Conservative. RMS prop. An optimization method closely related to Atom is RMS prop. A version with momentum has sometimes been used. Graves 2013. There are a few important differences between RMS prop with momentum and Atom. RMS prop with momentum generates its parameters updates using momentum on the rescaled gradient, whereas Atom updates are directly estimated using a running average of first and second moment of the gradient. RMS prop also lacks a bias correction term. This matters most in case of value of beta 2 close to 1 required in case of sparse gradients, since in that case not correcting the bias leads to very large step sizes and often divergence, as we also empirically demonstrate in section 6.4. RMS prop lacks a bias correction term, which matters most in case of beta 2 is close to 1 to require sparse gradients. Assuming to preserve those gradients to avoid the vanishing gradient problem. AdaGrad, an algorithm that works well for sparse gradients, is AdaGrad. Its basic version updates parameters as delta t plus 1 equals delta t minus alpha times g sub t all over the sum of, okay, interesting. So it just updates the parameters based on the step size in the gradient divided by its own square? No, this, well, the sum of the squares. At all previous time steps. Note that if we choose beta 2 to be infinitesimally close to 1 from below, then the limit of v sub t hat as beta 2 approaches 1 is equal to t to the minus 1? What is it supposed to be? That's got to be a misprint. Oh, but t. It is t to the minus 1. Times this sum, this gradient squares. Eta grad corresponds to a version of Atom with beta 1 equals 0, infinitesimal 1 minus beta 2, and a replacement of alpha by an annealed version. Alpha equals alpha times t. Oh, yeah, it is missing them. There it is. The minus half, namely theta t minus alpha times t to the minus half times momentum all over the limit of the second moment as beta 2 approaches 1 equals theta t minus all that junk t times, okay, so we're replacing the mt and all that with the gt over, yeah, because we have this. Let's see, where did it define mt? Yeah. The gt over, yeah. Note that this direct correspondence between atom and atagrad does not hold when removing the bias correction terms. Without bias correction, like in RMS prop, a beta 2 infinitesimally close to 1 would lead to infinitely large bias and infinitely large parameter updates. Experiments. To empirically evaluate the proposed method, we investigated different popular machine learning models, including logistic regression, multilayer, fully connected neural networks, and deep convolutional neural networks. Using large models and datasets, we demonstrate Atom can efficiently solve practical deep learning problems. We use the same parameter initialization when comparing different optimization algorithms. Hyperparameters such as learning rate and momentum are searched over a dense grid, and the results are reported using the best hyperparameter setting. Experiment. Logistic regression. We evaluate our proposed method on L2 regularized multi-class logistic regression using the MNIST dataset. Logistic regression has a well-studied convex objective, making it suitable for comparison of different optimizers without worrying about local minimum issues. The step size alpha in our logistic regression experiments is adjusted by 1 over square root t decay, namely alpha t equals alpha over square root t. That matches with our theoretical prediction from section 4. Logistic regression classifies the class label directly on the 784 dimension image vectors. We compare Atom to accelerated stochastic gradient descent with Nesterov momentum and Atagrad using mini batch size of 128. According to figure 1, we found that the Atom yields similar converges as stochastic gradient descent with momentum, and both converge faster than Atagrad. As discussed in Deshie et al. 2011, Atagrad can efficiently deal with sparse features and gradients as one of the main theoretical results, whereas stochastic gradient descent is low at learning rare features. Interesting. Atom with 1 over square root t decay on its step size theoretically matched the performance of Atagrad. We examined this sparse feature problem using IMDb movie review dataset from Moss et al. 2011. We pre-processed the IMDb movie reviews into a bag of words feature vectors, including the first 10,000 most frequent words. The 10,000 dimension bag of words feature vector for each review is highly sparse. As suggested in Wang and Manning 2013, 50% dropout noise can be applied to the bag of words features during training to prevent overfitting. In figure 1, Atagrad outperforms SGE with Nesterov momentum by a large margin, both with and without dropout noise. Atom converges as fast as AdaGrad. The empirical performance of Atom is consistent with our theoretical findings in sections 2 and 4. Similar to AdaGrad, Atom can take advantage of sparse features and obtain faster convergence rate than normal SGD with momentum. Okay. Let's see, so that's the training cost. Iterations over entire data set. You got Atom, SGD, Nesterov, and AdaGrad. Multi-layer neural networks. Multi-layer neural networks are powerful models with non-convex objective functions. Although our convergence analysis does not apply to non-convex problems, we empirically found that Atom often outperforms other methods in such cases. In our experiments, we made model choices that are consistent with previous publications in the area. A neural network model with 2 fully connected hidden layers with 1,000 hidden units each and ReLU activation are used for this experiment with mini batch size of 128. First, we studied different optimizers using standard deterministic cross-entropy objective function with L2 weight decay on the parameters to prevent overfitting. Sum of functions method is a recently proposed quasi-Newton method that works with many batches of data and has shown good performance on optimization of multi-layer neural networks. We used their implementation and compared with Atom to train such models. Figure 2 shows that Atom makes faster progress in terms of both the number of iterations and wall clock time. Due to the cost of updating curvature information, SFO sum of functions is 5 to 10 times slower per iteration compared to Atom and has a memory requirement that's linear in a number of mini batches. Stochastic regularization methods such as dropout are an effective way to prevent overfitting and often used in practice due to the simplicity. Sum of functions assumes deterministic subfunctions and indeed fail to converge on cost functions with stochastic regularization. We compare the effectiveness of Atom to other stochastic first-order methods on multi-layer neural networks trained with dropout noise. Figure 2 shows our results. Atom shows better convergence than other methods. Training multi-layer neural networks on MNIST manages neural networks using dropout stochastic regularization. Neural networks with deterministic cost function. We compare it with sum of functions optimizer. Let's see, so SFO is the top one and Atom's the bottom one. Let's see. Convolutional neural networks with several layers of convolution pooling in nonlinear units have shown considerable success in computer vision tasks. Unlike most fully connected neural nets, weight sharing in CNNs results in vastly different gradients in different layers. Smaller learning rate for the convolution layers is often used in practice when applying stochastic gradient descent. We show the effectiveness of Atom in deep convolutional neural networks. Our convolutional neural network architecture has 3 alternating stages of 5x5 convolution filters and 3x3 max pooling with stride of 2 that are followed by a fully connected layer of 1,000 rectified linear units. Not that many in practice. Input image are preprocessed by whitening, and dropout noise is applied to the input layer and fully connected layer. The mini batch size is also set to 128, similar to previous experiments. Interestingly, although both Atom and AdaGrad make rapid progress lowering the cost in the initial stage of training, shown in figure 3, Atom and stochastic gradient descent eventually converge considerably faster than AdaGrad for convolutional neural networks, shown in figure 3. Dang. Shoot, up to 25 iterations. We notice the second moment estimate v sub t hat vanishes to zeros after a few epochs and is dominated by the epsilon in algorithm 1. The second moment estimate is therefore a poor approximation to the geometry of the cost function in convolutional neural networks comparing to fully connected network from section 6.2. Second moment estimate is therefore a poor approximation. As reducing the mini-batch variance through the first moment is more important in the convolutional neural networks and contributes to the speedup. As a result, ADAGRAD converges much slower than others in this particular experiment. Though Adam shows marginal improvement over SGD with momentum, it adapts learning rate scale for different layers instead of hand-picking manually as in stochastic gradient descent. Experiment. Bias correction term. We also empirically evaluate the effect of the bias correction terms explained in sections 2 and 3. Discussed in section 5, removal of the bias correction terms results in a version of RMS prop with momentum. We vary the beta 1 and beta 2 when training a variational autoencoder VAE with the same architecture as in Kingma and Welling 2013 with single hidden layer with 500 hidden units with soft plus non-linearities and 50-dimensional spherical Gaussian latent variable. We iterated over a broad range of hyperparameter choices, i.e. beta 1 member of 0 to 0.9 closed range and beta 2 member of 0.99, 0.999, and 0.99999. And log base 10 of alpha's member of -5 to -1. Values of beta 2 close to 1 required for robustness to sparse gradients results in larger initialization bias. Therefore, we expect the bias correction term is important in such cases of slow decay, preventing an adverse effect on optimization. Figure 4 values beta 2 close to 1 indeed lead to instabilities in training when no bias correction term was present, especially at first few epochs of the training. Best results were achieved with small values of 1 minus beta 2. Oh, going behind. I'm on page 8 now. Figure 4. I should have known that. This was more apparent towards the end of optimization when gradients tends to become sparser as hidden units specialize to specific patterns. In summary, Adam performed equal or better than RMS prop regardless of hyperparameter setting. Okay, Adamax. Extension, chapter, section 7. Extensions. 7.1 Adamax. In Adam, the update rule for individual weights is to scale their gradients inversely proportional to a scaled L squared norm of their individual current and past gradients. We can generalize the L2 norm based update rule to a L to the P norm based update rule. Such variants become numerically unstable for large P. However, in this special case where we let P go to infinity, a surprisingly simple and stable algorithm emerges. See algorithm 2. Now I'll derive the algorithm. Let in case the L to P norm, the step size at time t be inversely proportional to v sub t to the power 1 over p, where vt equals beta 2 to the power t times vt minus 1, t minus 1, v sub t minus 1, plus 1 minus beta 2 to the power p times magnitude of gradient to the power p. Oh no, that's probably just the Hadamard product again. 1 minus beta t, yeah, so we can pull out 1 minus beta 2 for the sum, leaving us with beta 2 to the power p times t minus 1 times the gradient to the power p. Note that the decay term here is equivalently parameterized as beta 2 to the power p instead of beta 2. Now let p go to infinity and define u sub t equals limit of v sub t as p approaches infinity raised to the power 1 over p. Then, I'm not following any of that. Yeah. Okay, u sub t equals limit p approaches infinity, v sub t 1 over, which corresponds to the remarkably simple recursive formula u sub t equals max b2 times u sub t minus 1, where, or given, or no, the max between those two. It's interesting. Is that the magnitude? Yeah, recursive formula with initial value u sub 0 equals 0. Note that conveniently, though, we don't need to correct for initialization bias in this case. Also note the magnitude of parameter updates has a simpler bound with Atomax than Atom, namely, the magnitude of delta t is less than or equal to a. Temporal averaging. Since the last iterate is noisy due to stochastic approximation, better generalization performance is often achieved by averaging. Previously in Mullins and Bach, 2011, Polyak, Rupert, averaging, Polyak and Juditsky, 1992, Rupert, 1988, been shown to improve the convergence of standard stochastic gradient descent where theta t is equal to the inverse of t times the sum of the parameter space over k. Alternatively, an exponential moving average over the parameters can be used, giving higher weight to more recent parameter values. This can be trivially implemented by adding one line to the inner loop of algorithms 1 and 2. Theta t is assigned beta 2 times theta t minus 1 plus 1 minus beta 2 times theta t with theta 0 equals 0. Initialization bias can again be corrected by the estimator. Theta t equals theta t over 1 minus beta 2 to the power t. Conclusion. Okay. We have introduced a simple and computationally efficient algorithm for gradient-based optimization of stochastic objective functions. Our method is aimed towards machine learning problems with large data sets and/or high-dimensional parameter spaces. The method combines the advantages of two recently popular optimization methods, the ability of AutoGrad to deal with sparse gradients and the ability of RMSProp to deal with non-stationary objectives. The method is straightforward to implement and requires little memory. The experiments confirm the analysis of the rate of convergence in convex problems. Overall, we found Atom to be robust and well-suited to a wide range of non-convex optimization problems in the field of machine learning. Okay, special things. Hmm. Hmm. Okay. It's just appendices after that. Convergence proof. Be good to look at eventually, but God. Oh, damn, that's hairy. Simplify the notation we define. Let's get geometry. Yeah, that's it. Yeah. Well, that paper wasn't so bad. What should we read next? Let's see. Okay, we got that one. Commercial bottleneck. Atom optimization. Let's see. I already read visualizing lost landscape. Well, I guess I didn't read the rest of it, or just read the first couple pages. Okay, so that's definitely another good one, but I already know the fundamentals of that one. Yeah, filter removal lost plots. Depth, promise up. Shortcut connections rescue. Makes neural networks trainable. See, that's about because adding the residuals increases trainability but reduces detail. I mean, I feel like it's obvious that it's compressing the latent space, but we gotta do that entropy study first. Okay, and this is another, just be 9 pages. I'll do that another time because I'm feeling sleepy. Okie doke. See y'all another time.